Modern cellular networks are designed for extreme density. In urban centers, thousands of overlapping cell sites process terabytes of data every second. But travel just a few dozen miles outside that dense core, and the fiber optic grid abruptly stops. The expansion of traditional 5G hits a physical wall. In mountainous terrain, deep rural zones, and regions prone to natural disasters are structurally hostile to standard cell towers. This chart illustrates the core problem. As we move further from urban centers, the cost to lay fiber spikes. Meanwhile, projected revenue remains flat. Pushing terrestrial infrastructure out here creates unmanageable capital expenditures and decades-long return on investment cycles. Historically, operators tried to solve this geographic gap using satellite connectivity, but it was treated as an emergency fallback or a niche solution for maritime routes, entirely separate from the main network. Relying strictly on terrestrial expansion to achieve ubiquitous 6G coverage is no longer viable. Solving the coverage gap requires adding an active layer to the network architecture, rather than pouring more concrete. As networks evolve towards 6G, non-terrestrial networks, or NTN, are moving from isolated backups to active, integrated components of the operator's core topology. Pulling a layer of low Earth orbit satellites into the architecture creates a global umbrella. These satellites establish direct data links back to the central core. This bypasses the CapEx wall, providing rapid coverage and systemic resilience during terrestrial outages. But integrating a space-based layer directly into a ground-based core creates a significant engineering tension. Cellular protocols are built for millisecond response times. Introducing satellite distances can break standard performance KPIs and disrupt latency-sensitive services. While launching hardware into orbit is a major logistical feat, the primary engineering hurdle for 6G is system-level integration that maintains operator performance standards. When discussing satellite integration, network engineers focus on one primary technical hurdle: end-to-end latency. Look at this side-by-side comparison. On the left, legacy geostationary satellites sit tens of thousands of miles away, resulting in ping delays well past 600 milliseconds. Cellular protocols cannot accommodate those delays. The connection times out and fails. On the right, we see the advantage of modern LEO networks. Operating much closer to the Earth's surface, the signal transit time shrinks to a loop under 50 milliseconds. This confirms LEO latency is within acceptable limits for broadband data. These LEO links handle high-bandwidth enterprise workloads and mission-critical emergency services. Shrinking the latency window shifts the entire deployment model. Operators can upgrade satellite from a passive limitation to a high-throughput active layer of the network. Because orbital latency is no longer a disqualifying factor, operators can now proceed with active hybrid integration. Even with data solved, maintaining high-quality voice service over remote distances remains a difficult integration challenge. Building a full radio access network just to blanket isolated rural pockets with voice coverage is financially impossible. The transitional strategy for 6G voice continuity relies on voice over Wi-Fi, combined with a satellite backhaul. This diagram traces the exact routing path of this hybrid voice connection. The packet moves from the user's device, routes through a local Wi-Fi access point, and transmits to the LEO constellation. The return path completes the circuit. The satellite beams the signal to a ground station, routing it into the operator's IP multimedia subsystem, or IMS core. This allows the operator to maintain control over service quality and the direct billing relationship. This routing mechanism removes the need for traditional terrestrial cell sites. It also provides indoor service using the local Wi-Fi router as the access point. In markets where direct-to-device NTN integration is not yet standardized, this VoE Wi-Fi method serves as an immediate bridge. By running VoE Wi-Fi over an NTN backhaul, operators can deliver continuous voice service while decoupling their coverage map from ground infrastructure costs. Building the physical architecture is only the first step. The operational logic, how the network monitors and heals itself, must also adapt. This dashboard shows what happens when you apply traditional terrestrial metrics to a hybrid setup. Legacy KPIs are designed for sub-10 millisecond latency and zero-tolerance jitter margins. When processing a satellite data stream, the dials spike into the red. The network logic interprets the standard physics of a LEO connection as a terrestrial fault. The operational consequences are immediate. Network Operations Center boards flood with false alarms, and automated tools misallocate resources to fix a non-existent tower issue. To prevent this, operators must develop NTN-aware performance thresholds. Engineers must recalibrate baseline expectations for latency, jitter, and handover degradation to account for the space link. Standard availability metrics also need to be redefined for hybrid scenarios, as satellite capacity fluctuates based on orbital positions. Radio optimization strategies must evolve to track moving LEO passes, replacing the old logic of monitoring fixed geographic azimuths. A hybrid network will collapse operationally unless its self-monitoring KPI logic is rewritten to distinguish between a failing tower and a functioning satellite. With the technical integration solved, the economics of network monetization change. The high financial cost of heavy infrastructure rollouts is replaced by the agility of hybrid capability. Operators can now execute a strategy of selective rural coverage expansion, leveraging NTN partnerships to deploy exactly where demand exists. This changes how operators target enterprise-focused rural connectivity, such as remote mining, agriculture, or logistics. They can provide service to these specific zones without building out the empty miles in between. This capability allows operators to bid on institutional service contracts in remote regions they previously abandoned as unprofitable. The business advantage lies in ownership. The operator leverages the satellite provider's hardware, but retains the direct billing relationship with the enterprise client. Hybrid NTN transforms rural coverage from a mandated financial loss into a targeted enterprise strategy. The window to execute this strategy is narrow. Independent satellite providers are already expanding their direct-to-consumer reach into underserved regions. This presents a three-part choice for cellular operators: compete, ignore the trend, or integrate. Attempting to compete directly or simply ignoring the trend carries severe risks. Operators will lose enterprise accounts and surrender their control over end-to-end voice services. A collaborative hybrid model is the logical path. It allows operators to protect their core accounts while expanding their perceived global coverage map. Satellite has transitioned into a direct extension of the core operator architecture. As 6G research accelerates globally, the operators who master this system-level hybrid integration early will dictate the future of wireless networks. Those who cling to terrestrial-only models will be left behind.